Professor Zodruch. So, maybe you know this person?
Maybe not. Добрый вечер, студенты и преподаватели, уважаемые коллеги. Я сам работаю в САГе, возглавляю эту самую кафедру физики полета. Но сегодня не наш час, а вот мы пригласили наших уважаемых коллег. Я хотел бы представить их по-русски, а потом перейдем на английский язык. Профессор Зодрух, Яхим Зодрух. Он долгое время, карьера его, наверное, пример в западном мире подходов, когда люди, в принципе, перемещаются с одной фирмы в другую. Он отработал, наверное, где-то лет, закончил, естественно, университет по классу технологий, хорошо очень знает вопросы о Вьетнаме, работал больше 10 лет в компании Airbus, президент по технологическому развитию. Собственно, это то время, когда как раз Airbus набирал силу. Вы знаете, что первый аэробус А300 появился в районе 75-76 года, наверное, только, да? В то время, когда мы здесь учились, сидели в классе. Первый аэробус. За это время, представляете, компания стала второй в мире, а по некоторым видам даже первой компанией в мире, в области пассажирских самолетов. Это то время, когда такие люди, как Зодрух, единомышленники, соорудили план, и двинули технологии, понимая, что только через новые технологии возможно успешно конкурировать. После этого он переместился лет 10-12 позже, компания уже была на плаву, он перешел в Национальный исследовательский центр Германии, ДЛР называется. Это даже не эквивалент ЦАГИ, то есть сложить вместе возможности ЦАГИ, ЦИАМ, ВИАМ, частично ГосНИАС. Это будет центр ДЛР. У них сегодня работает около 10 тысяч инженеров, исследователей, сотрудников. Он многие годы, последние лет, наверное, 15, являлся руководителем, по сути дела, этого центра. И сейчас он только-только вышел, можно сказать, на пенсию, и у них принято достижение пенсионного возраста уходить на какую-то не административную позицию, он остается членом исполнительного комитета ДЛР. Кроме этого, для нас сегодня это особенно важно, когда мы думаем, а где наше место и как нам развиваться в России в плане научных исследований. Он лет 10 последних возглавлял такой совет по стратегическим исследованиям в Европе. То есть совет, который определял, собственно говоря, приоритеты, куда двигаться, какие темы развивать, куда техника должна двигаться в плане совершенствования. То есть это такой мозговой центр Европы, и профессор Зодрух возглавлял его последние десятилетия. И сейчас небольшой секрет, поскольку у нас личная еще дружба с ним, так, многолетняя, мы договорились, что он и нам поможет в плане определения своего пути собственного в России, чтобы мы достойно работали, мы уже работаем, но нам надо сделать еще один шаг к полному равенству и занять достойную позицию, которую мы заслуживаем, так, в технологическом мире. Поэтому у нас 2 дня шли очень плотные взаимодействия такие, семинар, можно сказать, или непрерывное совещание двухдневное, где наши ведущие специалисты, наши самые продвинутые ученые, аналитики, включая Ильич, например, Шустер. Мы занимались тем, что это был мозговой штурм по поводу того, куда нам дальше двигаться, что делать, как заинтересовать вас, молодых ученых, будущих ученых. Вот, какая система должна быть, чтобы это мотивировало вас, так сказать, не в банки бежать, не продавать что-нибудь, а, так сказать, заниматься самым достойным делом, так сказать, то, чему учили в школе, что вы хорошо умеете, задачи решать, математика, физика, а продолжать это делать именно по линии развития, создания новых технологий. Вот, ну вот такая преамбула. Я, наверное, еще представлю второго гостя. George, I'd like to introduce you also.
Yes.
So we have Professor Zodrucha who is preparing his presentation, I guess. This is Professor Zodrucha. And George Bridl, это тоже мой старый друг, имеющий корни, между прочим, российские. Где-то он там нашел, что 200 лет назад его родственники служили при дворе Петра Первого. Вот. И он даже нашел на каком-то старом кладбище могилу с фамилией Бридл. Вот. Он сам швейцарец, живет в Швейцарии, но работал долгие годы, последние, наверное, 15, вице-президентом компании EDS, такой мощный холдинг европейский, ну, как бы главный конкурент Боинга в Европе. Вот. И, конечно, очень много знает про самолеты. Вот. Он в основном работал по программам истребителей, файтер и другие разработки европейские, он практически их вел. Вот. Но сейчас и Джордж тоже, как бы ушел немножко в сторону. У них не принято вот в пожилом возрасте как бы брать на себя административную нагрузку, а вот в качестве источника мудрости, вот, принятия правильных решений, вот они продолжают взаимодействовать со своими организациями. Ну и тоже вот согласился очень любезно нам помочь в выработке нашего собственного стратегического плана исследований в России. Вот, кстати, этот план мы будем через неделю защищать перед нашим министром. То есть вот, видите, результаты кооперации. Мы его разрабатываем вместе и потом представляем нашему правительству. So this very short introduction. Thank you very much. I said very good words about you.
Okay, thank you. You know, I know a little bit of Russian, so.
So at this time, George,
Very
you will start, and thank you very much.
Thank you, thank you, Sergei, for this brief introduction. And very heartily welcome here, because it's, as I have learned, also part of his home. Anyway, professors, ladies and gentlemen, I'm pleased to be here and in such a prestigious place. I have heard a lot about, and it was like, you know, some of the brains of science in aviation in Russia. So we are the first time here. Thank you very much that we can do it. Now, I will be relatively short because Joachim's presentation will, of course, be the core and the most important thing. But nevertheless, I would like to briefly introduce ourselves again, because we are working together in some kind of a consulting group, and we have all both have had a career in the aircraft industry. This means Airbus, and myself in EAS military aircraft. I have a Swiss career, he has a German career. So I'm just briefly introducing this group, which is a consulting group which has been founded already in the 80s in Switzerland, and we are quite international. We are, let's say, senior members and young members, so a very good mixture, we think, and I just briefly give you a short overview. So this Aerospace Project Development Group, you can find it, here, of course, as usual, in the website. It's a pool of aerospace knowledge, okay, since 1981, so we were also quite young when we created it. Nevertheless, now it has quite a past of 30 years. We have a company, we are roughly 40, an association, 40 members, and we have competence centers built around concept development, real start of airplanes, requirements, making the first drawing, and so on. Then we do have aerodynamics, performance propulsion, which goes to concept development. We have aerospace projects when we are going to consult or even develop projects within that center of competence. We have one very experienced in air traffic management. We are doing here work for the EASA, for instance. Then we have a very specific aircraft performance. We have some military aircraft partly where we are doing work, and some CFD, and a historical department, because I love history. I love to see old airplanes and all, so good, useful wind tunnels, and wind tunnels, and so on. So that is our mark. I would say it's economy, it's flexibility, confidentiality. We are completely outside industry. Our opinion is independent, no financial dependencies. And finally, we are also Swiss, although very international members from France, from UK, Germany, and of course Switzerland. I think he has presented already, Sergei, my colleague Lecция Zodrucha, myself also. It's a little bit shorter, and we have partly had same activities like presidents of this all over group, Council of European Aerospace Societies. So, what is AR? Just what I mentioned before. In fact, it was developed for this in the 80s, early 80s. We had designed this concept of a light combat aircraft, which was then materialized later on. I participated also in the Indian light combat aircraft. Then the Gripen came, the T-50 from Korea, and so on. So there were a few light combat aircraft. We did that concept up to 1985. And then in the US, we tried to do this in Boeing, but then for political reasons, we made this trainer aircraft, composite, all aerobatics and two pilots, or four with 2 passengers as a training airplane. That was a very interesting, good development, and it was later on produced abroad, not in Switzerland. And for this, we designed this RPP. It's an aircraft performance program, which is still unique. There are really aircraft performance programs on the market. We sell it a little bit everywhere, and we continuously adapt it to the recent IT requirements. That's the classical work done by our young members. People that are partly your age, partly older. They are masters and getting PhD and doing further development of that. So you see the network with these different centers of competencies. That's the aircraft performance program. By the way, we sell it as educational licenses to universities worldwide, and it has certainly gained attraction. It is very clear program. I mean, it's nothing new. It's based on flight physics of the aircraft. There is no dynamics in it, but nevertheless, it computes directly out of the actual aerodynamics. A good engine deck, of course, is required, the weight and so on. It's extremely flexible, so it's quite a good tool for teaching as well. So here's some data, for instance, 747, the 100 mission with all flap settings and so on, quite a complicated one, or an aircraft performance calculated with RPP based on actual data of an F-18 fighter and comparison with F-16. As you see here, the difference between subsonic superiority of the F-18, which is not surprising, and the supersonic is where the F-16 is, of course, better for conceptual reason. It's a different aircraft. So we do support civil aeronautics and air traffic management, as you see here. And finally, we do also some kind of applied research or applied work in wind tunnels, mostly for diploma work for students, some fluid mechanics and so on, participation in EU framework programs, partly it's clean sky, wind tunnel testing. We do have in Zurich, close to our office, from Professor Ackeret. You may know Professor Ackeret, who had the linear theory, the Ackeret equation in supersonic, and we had there still the first supersonic wind tunnel of the world in closed cycle. That was designed in 1934-35 in Zurich. So, ladies and gentlemen, that's it. I think I will give you an introduction. Please, welcome. Really good. The presentation we did anyway.
Okay, well, thank you very much, George, and oops, good evening from my side. I hope you're all awake. I know it's late in the evening, and how long time do you have? I mean, how long do you want entertainment? I know you have to go home for dinner. So I tried to make it short, but yesterday Professor Janichev told me, and by the way, could you give a lecture tomorrow? I said, yes, wonderful, I go and solve these equations there for you, but then I thought maybe it's too late in the evening. And since George already tried to sell you the products of ALR, you know, I thought maybe I share with you some ideas about, let's say, the future of aeronautics. And since I just learned that only, what did you tell me, 20%, 30% of you, once you finish your study, go into aeronautics, maybe I can stimulate a little bit to think about it, what you do in the future. Because I tell you, I mean, banking is boring. You know, you earn a lot of money, but it's a boring work in my mind, because you know, what is the intent in the end? It is better if you go into banking. You know, you go and support the aeronautical industry, and then you're a good person, but otherwise, that's... Anyway, if you think back a little bit on what we achieved over the past more than 100 years, and what you see here is Lilienthal unpacking his flyer, his glider aircraft. But I think what was important, and what he said was important, that, you know, once we learn flying, we enter into a new era of culture, a new cultural era. And if you think about it, how airplanes, and I'm thinking about civil airplanes, how they changed our way of living, how they changed the world, I think he was, as I said, over 100 years right in saying this is a new cultural era. But talking about the future is a very difficult thing. And there have been very famous persons who mentioned what could be done and what could not be done. And the prediction is dangerous. Because if the prediction is right, probably you do not live long enough in order to, you know, get all the praise and the clapping on your shoulders. If the prediction is wrong, everybody will point with a finger and you said, well, you didn't know what's happening. So I give you a couple of ideas what people were thinking in 1964. And I mean, this is only like, 50 years ago. Yeah? And 50 years ago, there were people thinking, you know, we will have, I cannot read it, a flying wing, like an aircraft like this, or hypersonic wave rider. This was a prediction, 64 to 84, so only 20 years in time. And some people were even thinking you have vehicles, ground vehicles running on an air cushion 500 kilometers per hour. Or the other things like laminar flow. If you are not familiar with any of the terms I mentioned here, please raise your fingers, okay? We can explain that. We don't have laminar flow. We have variable sweep on fighter aircraft, but not on the others. Auto control and artificial stability, we have computer networks. They thought we have computer networks. Now, if you think of this item, it was heavily underestimated. I mean, what we have nowadays is this global World Wide Web, which they even couldn't dream about in 1964. So this was a totally underestimation of the development, of the technical development in that field. They thought passenger airlines without seat reservation was a wonderful thing. I believe it's horrible, you know, because you have to run into the aircraft and fight for your seat. So what a bad idea. Aircraft life service life, 10 to 15 years, we reached today 25 years and more. So underestimated as well. And the last thing they thought is that you have supersonic or long-haul travel or inland travel in the US. And of course, we had supersonic aircraft, but for a very short time only. And also this prediction was pretty much wrong. And if you see who did it, I don't know if the names are familiar to you, but Lytle is a famous name. And this man was from what is called today Dassault, so also quite a high-ranking person. What I'm saying is beware of predictions. Okay, and this is another one from '87. I mean, we now advanced 20 years, and you see still the same dreams. Still the same dreams. Hypersonic aircraft, open rotor aircraft, flying wings. You can look a little bit closely. Prop fans we don't have, flying wings we don't have, and this is 30 years ago or 25 years ago. And we are still working on things, you know. Visions of today are still the same like 25 or 40 years ago or 50 years ago. This is some nice pictures. Before I come to the more serious things, I thought I'd show you some pictures to wake you up. What people believe, what is possible in the future. Airports or this, I don't know, Sergey, this picture down there, I don't know. But
Caspian monster.
I'm joking. Freighter cargo aircraft of various kinds, or airports built in the sea. Actually, we took off and started from one in Nagoya Airport, which is right into the sea, built right into the sea, like tanker aircraft, which feed fuel during flight, in-flight refueling, or other concepts like on the airport, because I mean we should not only look at the aircraft, but also at the airport. It's terrible nowadays if you go through security. This is a security tunnel. You just walk through and everything is done, including passport control and identification and security control, everything. This is formation flying, also an old dream, of course, or again, refueling in flight, or even takeoff and landing from larger aircraft in flight. This is one of the feeder aircraft, and this is another idea where you have passenger containers, which you simply switch between aircraft or from the airport into the aircraft. And what else do we have? Personal transport. Yeah, I mean, this is really another thing from Moscow. Because when I arrived, what is the airport? SVO. It took me 4 hours to come to Shukovsky from there. You know, I would have loved to have such a thing for personal transport. Well, I don't know, it was quite wet on that day, so maybe that's not a good idea. You see various ways of doing things, but also this is quite old. As you can see from something from the 50s, they also thought of personal transport at that point in time. And I know that Professor Chernychev loves high speed, and I love it too when going to Australia. You know, it saves a lot of time. So there are numerous topics and actually concepts where people are also working on at the moment in Russia, in Japan, in Europe, in the US. Actually, at this point in time, I wanted to ask you about what you think about the future in aeronautics. But since we are already quite late in time, I think I skipped this part because I would have shown a nice movie. What is the problem we are facing? And the problem looking a little bit forward into the year, let's say 2050. There are some people who are saying we are living in an age they call Anthropocene. And what it means is that the activities of the human being in terms of influence on the environment is as large as the natural influence on the atmosphere, on the environment. Looking into 2050, we know the prediction we will have, instead of, you know how many people live at the moment on Earth, roughly? 7 billion. 6 and a little bit. So, well, I didn't count them, but it is statistics I've seen the other day. So we talk about roughly 9 billion people. And what they see is that the concentration between poorer and richer regions will increase. So there's a sort of fragmentation between these two areas, and this might lead to a destabilization in this world. Now, reading recently, sorry it's German, but I explain it, this is from May 2012, a new report by the Club of Rome. The Club of Rome was invented in the 70s, so it's 30 years ago. And they were actually the first one looking at the global impact of more and more people living on this world, on this earth. And what they predict now is that because of GDP, productivity, natural resources are going down, you will not have the increase in people living in 2050. But at the same time, they also say we will produce more CO2. And there are some regions which still have a larger growth than other regions. And these are the BRIC countries. You know what the BRIC countries are?
Yeah.
No, you know. I asked the students.
I feel like students.
India and China. So they formulate a little bit different conclusion at the moment, but anyway, if it's 8 billion or 9 billion, it doesn't make a big difference. So what we need to do is that we need innovation and the development of these regions, these poorer regions. And in order to do that, you need energy. And the final conclusion is, and I tell you why I'm showing that to you. The final conclusion is you need to decouple the energy needs and the growth. And I think this is the topic also for aeronautics. We have growth in aeronautics over the next 20, 30, 40, 50 years, maybe more than we even predict today. And we have exactly the same problems with the energy, not only the supply, but also the impact on the environment. And this is why I think it's a good analogy, not only looking from the point of globalization, but also from the point of aeronautics. So if we take this influence, this human influence, maybe you have seen all these figures here, but you clearly see that from the time when they started to measure the temperature, you can see that there is a temperature increase in the medium of roughly 0.7 degrees or 1 degree. It depends on the models you're using. And somebody told me the other day that at this point in time, 30 years back, this lady was standing up to here in snow in this area. And I think we all see it in our daily life that there is a change in climate, although climate is a very long-term thing. The other point are the people and the travel habits of people and what can they afford. And there's a clear relation between the gross domestic product, so what you earn in a country or in this world, and the trips of the people per year. And if you look closely, you can see that in Russia you do something like, I don't know what, 0.5 maybe trips per year. That means each person in Russia travels once in 2 years. You see other countries like Italy, France, Australia, UK, USA, they travel at least 1.2 times per year. So this is not only an indication on the real gross domestic product, but you can from that deduct how much people spend for mobility. And as I know, as I learned, Russia would like to go up there, and this is part of big plans coming up in this country. Okay, and how about energy? If we look at the energy for aircraft, it is totally dependent on kerosene at the moment, on oil. And this is a development of the oil price from the 1960s into the late years here. And I very well remember when I started working at Airbus in this area here, we always said, okay, yes, the oil price is changing, but it will stay at the value of, I don't know, here, 20, 30 US dollars per barrel. And now we see what's happening, and this, of course, is related to the availability of oil, but also to the market price. It's very clear. So we have two issues here, availability and the price of oil, which certainly is a difficult thing for the airlines and also for us, of course, when traveling or when driving the car. I know Russia has a lot of oil, but in Germany we don't have any. Well, a little bit, but not very. And the last thing is decoupling of energy consumption and growth. And if you look at this chart, you see that the energy intensity over the years, when you look at various aircraft, piston-powered jet airliners, it's not marked what exact aircraft it is, but you see that there has been a lot done in terms of reducing the energy consumption of aircraft. And at the moment we are standing with an A380 in this area, and the goals you see almost all over the world is another reduction by the year 2020 by 50%. So this is the target in 2020. Quite a dramatic achievement, because if you look at what happened so far, and if you interpolate that into the future, you might get half of it, but not the full amount. So these are the challenges. And these challenges have been taken up by the group of airlines which are connected in the IATA. And they said what we want to do in the next 10 years, in the next 50 years. And they formulated that we improve efficiency by 1.5% per year. Well, I'm saying, yes, you do this, but your fuel burn did increase by 1.6% per year, if you look at it in absolute values. Secondly, they said, let's stabilize emissions from 2020. And stabilize emissions from 2020 means despite growth, you have no increase in fuel burn anymore. And for that, you need at least, from that point of view, 50% other types of fuels which are not increasing the carbon release into the atmosphere. And the last thing they are saying is that you need that they want to have an emission reduction and an absolute cut by 50% in the year 2050 related to the year 2005. And that means that all new products from now on going into the market need at least 50% fuel burn reduction. And I know, can you imagine how much 50% is? I mean, I don't know if you have cars or not, but if you look at the cars and what they are producing in terms of CO2 or using in energy, 50% is a lot. Furthermore, we just calculated the other day that apart from what you do on the aircraft, in 2050 you need to fuel, if this is true, all your aircraft with 100% biofuels. And I don't know if you realize what that means, but it certainly means that we need a lot of area in order to develop these green fuels. I know there are other possibilities, specifically in Russia, what kind of fuels you can use, but these are really very, very ambitious goals set by the airline industry. And of course, the researchers have to find answers. So, one of the answers is you will not be able to gain all these benefits, the 50%, alone by using new aircraft. You have to look at the air transport system. What is the air transport system? And I have shown this. Does it move? Yeah, it moves. I have shown this here. You are Department of Physics, right? Normally, the people from physics think the aircraft is a mast point in the air, right? What you see here is mast point in the air, moving, of course, from one center to the other center, and somehow they are in the air and they have to be controlled. So, in essence, the air transport system is the aircraft, air traffic control, and the airports, because the airports is where they take off. You know, the sources and the sinks in this graph here. So we can look at it in more detail and say who is influencing this air transport system. Of course, first of all, it's society, because we are traveling and we send cargo from location A to B. Secondly, it's the passenger, and sorry, I forgot. Society also influences air transport not only by traveling itself as a passenger, but also by some things like noise and other issues which are disturbing us. Then you have the airports, you have the industry producing goods, aircraft, etc. You have the airlines who operate this whole thing. You have air traffic centers, as I mentioned already. You need to do maintenance, and that is sometimes a different industry. And you have also the agency who make the rules for certification of the aircraft. And last but not least, in this country, in all the countries, we have these people who are coming from politics and who lift their fingers and say, well, I'm an important man. Because in German, wichtig is important. However, all these stakeholders, they have different interests. On one hand, you want economic growth. You want employment. You want profits, of course. Why would you have an airline? You know the saying, you know, how to make a big fortune. You take a small fortune and you open up an airline. No, the other way around. Sorry, forget it. I mixed up the point. Okay, so profits, market shares, and on the other hand, despite growth and employment, you want also environmental protection. You want a safe and secure flight, and you want low fares. So safe and secure flight means, of course, higher cost for all these issues, and low fares. You know, airlines want to make profit. You don't want to pay so much. Comfort, we talked already about. So these are some of the issues where we have to work on. The challenges and the opportunities are, of course, the efficiency of the system, of the aircraft, of the ATM, the economy in the end, as I said, profit. It is the capacity. You have to, this business is growing. The level of service, as I already said, you know, not everybody is comfortable with finding a seat in a very densely populated aircraft. It's the safety and security issues, and it's, of course, the young people, because all what I have shown so far and what are the challenges only can be managed by the young ones, because we are looking forward for the next 20, 30, 40 or 50 years. As you know, aircraft building, design and building is a very, very long process. And last but not least, it's ecology. And I want to expand a little bit on the ecology because I started with this. If you look at the ecology side, what is it? It is, of course, also connected to maintenance. You use maybe toxic fluid in order to strip the paint from the aircraft. It's the land use. It's the manufacturing processes, of course, also. But then it comes to the operation of the aircraft, and this is emission and noise. That's, and yeah, of course, at the end of the aircraft, you have to somehow recycle it, and that's part of the story, of course. Let's concentrate on the emission side. And on the emission side, we have today CO2, we have contrails. Professor Janicek likes contrails, he has nice pictures of that. We have NOx's and we have soot. And of course, soot are part of the process of building contracts. Let's concentrate on CO2 because CO2 is directly related to fuel burn. And I don't know what you have done so far in your studies, but I thought this is simple stuff. Breguet formula, I guess everybody knows it, but I use it anyway because I think there are some interesting features in there. You know the Breguet formula, trip fuel per distance relates to your engine performance, your SFC, specific fuel consumption, to your weight of the aircraft, W, and to the aerodynamic performance, Mach number and lift over drag. Breguet, yes, exactly. If you look at that, if you look at the weight side, for a typical, let's say, long-range aircraft, you have on the weight side 30% roughly primary structure. And the reason why I show you that is everybody is talking about these wonderful composites and they reduce the weight by 20%, but 20% of the 30%, not of the total. Secondly, you have, of course, the fuel in there, which is, if you can reduce that, you can reduce that as well. And last but not least, you have all these wonderful items like people, but this is only 11% of the total aircraft. And you have the equipment and systems. And I mentioned that already yesterday during dinner that in some aircraft nowadays you have first-class seats or business, I don't know exactly, which weigh like 300 kilos. Now the poor designers in the factories, they fight for 50 kilos or maybe even 10 kilos only in order to reduce the weight of the aircraft. So you have to see all this in relation to technologies which are potentially possible in the future. The SFC, the specific fuel consumption, relates on the internal and on the external flow of the engine, the thermodynamics and the propulsion efficiency. We come back to that later on. The drag, aerodynamics. There's a couple of parts, of course, the viscous drag and the induced drag. Technologies are in the minds of people, like laminar flow or like winglets or whatever you have. And then you have smaller parts in interference drag, wave drag, parasitic drag. So that is how your shape is actually manufactured in the end. So let's have a look. What do you think you can gain in these areas from new technologies? Systems. If we look on the system side, and what I'm showing you now, the numbers you see there, like 3 to 5%, these are collections of papers I have seen in the past where people say, well, I believe that in 20 or 30 years we can achieve another 3 to 5% on the total aircraft, on the system side, with various issues. One, for instance, is using fuel cells. What I show you here is not what I propose for civil aircraft, but what has been done by the DLR in terms of a little bit of motion of fuel cells, and that's the first glider, motor-powered glider in the world taking off and landing only with the fuels, only with the fuels. So no suspenders and belts, no batteries in there, only fuel cells. Of course, you can do much more with the fuel cell. You can use it for your accelerated power unit, the APU, but also you can use it for driving your flaps and tracks, etc., etc. But we also did experiments, successful experiments, where we used a fuel cell for powered landing gear. That means you don't run your engine anymore when you taxi, but you can do it with this electric power. Saves emissions on ground. Okay, systems. Next is the engine side. And of course, you might be very familiar with the old and new trend using open rotors. I guess also Zagi has been working on that in the past and is working at that at the moment. the potential of reducing the fuel burn by another 15 to 30%, and that relates directly to the CO2 fuel burn. But you also see that there are some issues connected to that. There's a noise issue, there's a safety issue if you lose blades, and you can get around some of these items by like noise, by reducing your cruise speed. So this is something you have to work on, because I don't believe that society will accept a higher noise for a lower fuel burn. So you have to balance your design. That was the engine. Then we have structures. People believe you can reduce your primary structure up to 15%. I come back to my very simple calculation. 30% of 30% is 9%. Now maybe you can, by snowball effects, do a little bit more, but it will be very difficult to achieve 50%. So the challenge really is, if this is the weight and the cost, you are sitting here at the moment with composite technologies, but the metal guys are not sleeping. And the metal guys in the future might be somewhere at -10% in weight. So to get the full potential of composites, you need also to change the design of the structure. And then maybe you end up here. But in order to do so, you have to look at the total development chain. You cannot simply take the material and try a new design, but you have to start with the fibers, with the resin, and then develop the whole chain up to production. Because it's all connected to cost. It's not only the weight, but it's also the cost. If you cannot afford to put this on the aircraft, nobody will buy it. Okay. Structures and aerodynamics, last but not least. I just put two things here. One is laminar flow, of course, 120 years old, but not applied on any commercial aircraft. Or maybe 130 years by now. And the other one is maybe you can gain, if you have the right technology, something from configurations. So laminar flow challenges are quite clear. It is not an aerodynamic problem any longer. It's a problem of aerodynamics, of structures, of systems, and how to combine and integrate that into an airframe. And so you need not only the aerodynamic persons, but also the materials production, etc., etc. And last but not least, also operation. Because if you have a flight with this wonderful laminar technology using 10% less fuel, so you put 10% less fuel into your tanks, but unfortunately you lose laminarity because, I don't know, some insects or ice crystals or whatsoever, and you have to go down into the Atlantic Ocean. This is not the idea of laminar flow. So operation of this is quite a problem still. Okay, the challenges are addressed, of course, and last but not least, because everybody loves configurations, so I thought maybe I'll show some of them as well. Although I say, why do you want to have these configurations? There must be a reason behind it. Form follows function. So what is the function? First of all, the requirement. And out of the requirement, you might get some new configurations. And you see some ideas here what you can do. Of course, connected with this is you have a pressure cabin, but you don't have this ideal shape of a circle. Thank you. The other one is, of course, the certification. You have to get people out in 90 seconds. Can you develop a family concept? You know, nowadays people, if they develop the first aircraft, they cut it, and then they extend it, and then they have a family sort of concept. It's quite difficult here. So all these issues have to be taken into account. And airport integration, if you look at this in terms of, let's say, 300, 400 passengers, you get an aircraft with 100 meters span. It doesn't fit on any airport, normal airport nowadays. So all these issues you have to take into account, but again, people work on them. So if you take all these topics here, there is a European program which said, okay, let's focus all our technologies into demonstrators. And so this program, it's a 2 billion euro program. I don't know how that relates to rubles, but it's a lot of rubles. And they have developed the demonstrator concept, like for the smart fixed wing of a regional aircraft, etc., etc. I'm not going into detail. And along with that, they also formulated, if I would produce products out of this, what would the product look like? And so, and what characteristics would it have? So if we look at two products here, which is a typical single-aisle aircraft or a regional aircraft, they said, well, we are ready to achieve CO2 20%, which is fuel burn, or on a regional, even 40% fuel burn reduction with these technologies. Now, we did a little exercise here, looking at a 70-seater aircraft, 3,000 kilometers. And we said, let's have a 20% engine SFC improvement, which is below the open rotor, but which is higher than a geared turbofan, which is nowadays in the market. So it's already an ambitious goal. I hope you agree. The second one is 20% drag reduction. And I remind you, 15%, if at all, comes from laminar flow. I don't know where the rest comes from, but I just give you, for this exercise, 10% weight reduction. This is at least 15-20% structural weight reduction, primary structural weight reduction. Ambitious goals. Now you can put all this, you can increase aerodynamic tricks like wingspan, aspect ratio. If you do all this, you come up with certain numbers, and if you take these numbers, and even if you take snowball effects into account, you come to a result of 37% fuel burn. 37. So I wonder, I mean, it's close to 40, I agree, but these are extremely ambitious goals already. And what I'm telling you is, and this is why we need you, is we need new and brilliant ideas in order to achieve even the 50%. Okay, you can do more. I talked about the air transport system. So you can do more on the operational side. And of course, there is the flight guidance area. A lot of things you can achieve. Some numbers are given up there. Specifically, we have in Europe, and I don't know about Russia, but we have the problem of the air traffic control system, and you see some numbers there with more than 20,000 flights, but we also have over 27 different air transport controllers in Europe. So this needs to change, and one of the changes is the European program CESAR, and the idea is to have one system to reduce the cost to half the cost, and to have overall, at the same time, a 10% fuel burn reduction of European flights. So this is one thing you can do, and the other thing you can do, of course, what I have shown you earlier. Some people are dreaming of air refueling in long distance or formation flight, and the extrapolation in how much that could bring is 10 or even 25%. We haven't done detailed work on this, but at least it's something which could come up in the future. So these formation flying, multi-stop flights bring a certain improvement, but all this is research of the future. Okay, the last thing you can do, of course, in order to reduce CO2, you don't reduce fuel burn, but you reduce CO2, is using biofuels, alternative fuels. And there have been a number of feedstock starting from grain or maize, but of course this gives the discussion what they call, it's the tank or a plate where you eat from, you know. So this is the plate and tank issue. Of course, this is a no-go, absolutely no-go. So they're looking at the second generation Jatropha plants or algae even for producing biofuels. A lot of research is going on in that area. And actually in Germany recently there was a project where for 6 months they had a trial with a normal passenger aircraft flying from Hamburg to Frankfurt, where on one engine there was 50% biofuel. The idea was to look at what happened to the engine, the seals, etc., and how to organize all this. It was an interesting thing. It also has shown that you even reduce further your CO2 because this biofuel had higher energetic value, and you reduce the particles which are coming out of the engine as well. So it is good for contracts as well. All this, these wonderful figures of 50% or more, the question is, what does it do to the overall fuel burn of all the aircraft flying around the world? Any idea how many aircraft above 100 seats are flying around the world presently? Roughly.
20,000.
Above 100 seats, it's only 17,000, 18,000. Only. I had a teacher, he always said, you know, he is not satisfied unless the sky is dark with airplanes. I'm not sure if that is a good idea, but anyway. So if you do this and you look into the next 50, 20, 30 or 40 years up to 2050, and you would say, okay, we have a growth in this aeronautical business like 3 to 5%, increasing the 17,000 in 20 years or 15 years to 30,000. So increase your aircraft. Then, of course, connected to that, you have a fuel burn. And since they are old aircraft flying around and you introduce newer aircraft, the fuel burn and the transport capacity is slightly different. Now, the question is, if you introduce aircraft like 787 or Superjet or whatever, what else can you do? And this is the next curve. And then you can do the reverse and ask yourself, what would happen if I introduce goals like the 50% for all the aircraft sold from the year 2020? And you get the light blue curve, and then you can drive it even forward and say, I also introduce now air traffic management systems, and you come to the lower curve. And what you see here is actually the result that despite the growth of the system, you are almost stabilize your fuel burn or your CO2. And this is exactly what was a requirement, you remember, from the very beginning. But it's not enough, so you introduce some biofuels. It does not reduce fuel burn again, but it reduces CO2. The point is only that in the end, you remember the 50% absolute reduction. In the end, we have a large gap in order to fulfill the airline's requirements for the year 2050. Nobody knows at the moment how that is possible, except, as I said earlier, you have 100% biofuels, but even with that, I doubt that you reach this amount. So then, there was ACARA, and of course they put down a lot of goals, and now one could ask, where are we standing today? This was in the year 2000. The idea was to reduce fuel burn by 50%. Now we have the year 2010. What did we achieve? And without specification of the aircraft, but in CO2 or in fuel burn, in a certain technology demonstration, you can show that we achieve between 60 and 80% in fuel burn if we would introduce this technology on a new aircraft. The same is true for NOx. For noise, also quite an improvement of almost 80%. It seems possible with today's technology. And what it says is that we have done already in the research that has been performed over the last years, and which will go on over the next 2 or 3 years, we already achieved quite a good level of achievement with respect to this vision we developed. Okay, I'm not sure if I show that because people are getting nervous, I have a feeling. And I would like to skip that for the moment and go maybe to the last slide. Or almost to the last one. and say what is now in Europe. The idea which has been developed now in Europe is again a new vision which extends to the year 2050. There are a couple of items in there, but that is we have to look, of course, at the total air transport system, and it's for Europe a priority in terms of technology development. But we also need the right infrastructures. And when I talk infrastructure, it's wind tunnels or ATM simulations or even flight test research aircraft. We also need to support the research and technology mechanism, and that means the cooperation between the various stakeholders who work on the total system. We need people. And this is, you remember I told you in the very beginning, we need you, young people, in order to develop all of these new exciting things, in order to make this global business better, and supply chain, etc., etc. So you could ask now yourself what products we need to develop, if it's a shorter A320 or if it's a longer A320. You can speculate about that. I mean, the wing builders would be happy, you know, but you also could look at more realistic configurations like this, or like the concept plane, which Airbus is working on at the moment. It all looks futuristic, but you have to ask yourself, what does it do, and does it really fulfill the requirements we set in the very beginning? You know, they have these wonderful cabins. I'm not even sure if I would like to fly in these, where everything is sort of open. It's like a flying carpet in the end, you know. But we also need to look at cargo concepts, of course, because cargo is at least growing also at 7 or 8 or 9%. Yeah, okay, that's a different cargo concept. Okay. What is very popular nowadays is not only to look how you can get with the aircraft from airport to the other airport, but the intermodal traffic, that is aircraft, cars, trains, etc., etc. That's one way of doing it. The other way, of course, is aircraft-airport interaction, very important. If you think about the A380, it doesn't simply fit on all the airports, so you have to take that into account as well. But also how to get to the airport. And I told you about my experience with your airport and coming to Shukovsky. Okay, last but not least, what we have been developing here is, yes, a very, very ambitious plan, but I think we need to look more into details of this green scenario, the CO2 or NOx or noise-reduced aircraft, because the technologies are not readily available for that. How do we do this? We need to spend more on fostering the creativity and the innovation. There is the tendency, at least in Western Europe, that people work too much on application-oriented issues and too little on thinking of new ideas. I take the example of laminar flow. It's old. It's old. Where are the new ideas in aerodynamics? I ask you. Maybe you can give me the answer. What do we do? I mean, we have achieved tremendous things with transonic wings and whatsoever. But at the moment, this is the last barrier in aerodynamics. Where are the new ideas? And last but not least, of course, we have to balance, and this is our industry, we have to balance the windows of opportunity with regard to what technologies you have in your drawer that you can include in your aircraft, but also, do you have enough money for doing that? Because it's not free. And so the end is, are we always looking at the entire air transport system and developing a sustainable system, aircraft, air traffic control, airports, where we have more integration and more interpolation between the various areas. And with that, I would like to thank you for listening, and maybe just one idea of how you can go often blended. So, time for questions or not? I don't know.
Excuse me, sir.
Yeah.
My first question, I have two questions.
Yes, good.
One is technical. ICANN has made an estimation of the number of transport aircraft increasing by 5% annually till 2020, and it has made a plan called Vision 2020, right, as part of the strategic research agenda. Do you see glass laminated aluminum reinforced epoxies replacing carbon fiber reinforced polymers as chief structural material for which of these two do you think has better fatigue load characteristics with low production costs?
Well, these are three questions. One, I mean, low production costs. And these, I mean, first of all, you mentioned this 5%, which has nothing to do with composites, of course. I mean, the 5% in the end is a market forecast by Airbus, by Boeing, by maybe United Aircraft Company. They all come up with 5%. But what they forget, and this is what I wanted to make clear a little bit, is if you double the amount of aircraft, it's fine in the air. But when you come to the airports, the vicinity of airports and the ground handling, you create a problem which at the moment nobody is really solving. Right? So you have to look at the total system. That again was one of the remarks I had concerning your composites and the fibers you're using. That was your question, I understand. I'm not sure what will happen in the future, to be honest. I know that everybody is wild on composites. And if somebody from Airbus, Boeing, or United Aircraft Company comes in next time, or Mitsubishi, or whoever, ask them, because you have seen in the literature that in the earlier aircraft you have 20%, let's say, amount of composites, the new aircraft have 50%. What is the effect on the overall performance of the aircraft? Ask them. And then they will tell you, well, you know, I'm not a specialist. I don't really know exactly, but I know that this and this and this, and overall we have 50%. And the point is, I want to make is that at the moment, most of the people use design methods for metal and apply it to composites. So we have not the competence, the full competence, of course. I mean, this is black and white now, okay? The full competence of using the material to its full potential. And number one. So, and that is related then to the cost as well. Number two is composite really the answer for all aircraft? It might be for long range. You have a low cycle per year, like typically 2,000 cycles per year, takeoff and landing cycles. But for a short range aircraft, you already have double the amount, 4,000 or maybe even more, depending on the utilization of the airline. And that means you have not only different cycles, but you have the problem of potential damage on the ground, or through a bird strike or whatever happened, or hail, for instance. And the maintenance and repair costs, and we talked about unpaved runways, of course, it's another problem. If you look at all of this, you have to make sure that in the end there is a benefit for the airline in terms of cost, and the costs are not only the acquisition cost, but also the maintenance costs, repair costs, whatever is in the MRO cycle, maintenance, repair, overhaul. And you need to balance that. And if this is positive, then yes, you will have composite in the next short-range aircraft. But I can tell you that at the moment the chances are maybe 60-40. 60 for composites, 40 for metal. And the metal guys are not sleeping. I have shown you this picture where also metal could be developed. So it depends. What you can do is, of course, in terms of corrosion, you have a much better resistance, that is clear. And this is one of the arguments they are using. The second argument, of course, is that you can, with this directional forces you can introduce into the material, of course you can control, if you can design it, control your twist and your wing twist, I mean, and your bending, etc., to a certain extent, which gives you a lighter airframe. But you need to be able to do this. And this is sort of at the moment where we are standing. And I don't see a new material other than carbon. If that was your last question. At the moment. At least not for primary structures. Sorry, long answer for a short question. Yes?
I want to ask you about the future of CLS flying boat, such type of characters. They have a future or not?
That's a good question. It's a niche market, in my view. And when I say a niche market, I mean you have only a number of aircraft you can sell. I don't think it's a large market globally. For some countries it might be of interest, but globally I think it's a niche market. Like balloons and whatever ideas everybody has.
Now we have 2% for CLS, 2% for 1, 2% for 4.
If you think, I don't know how much a development of such a type of aircraft is, but I mean, it least costs also a couple of billions, right? 2, 3, 4 billions. And if you sell, I mean, it's an easy thing. If the development costs are 3 billion and you sell 200, you will not be able to sell it because nobody can afford to pay for it unless you have government support. Because it's vital for security or etc. That's my personal opinion. I'm really not an expert on this. And I have seen very little also in terms of market forecasts in this one. But from what I have seen, such an airplane never appeared. But don't be sad. I mean, also I have to admit that all the market forecasts are based more or less on the products a company has or would like to develop. Don't believe market forecasts are the sort of absolute truth. It's sort of also psychological. Okay. Yeah.
Sorry, question. Mr. Zodrucha, you were talking about biofuels.
Yeah.
You showed us some curves, but is it true that the gap you were talking about in Europe, they think you are going to fill
This gap.
yes, this gap you're going to fill using the carbon neutral effect.
Yeah.
So you say that the crops or algae, whatever you grow, when they grow, they absorb
Yes.
from the atmosphere
CO2.
CO2.
Yes.
And this CO2 then released in flight,
Yes.
you can compensate it. And
Yeah,
you
not 100%.
not 100%, but like up to 80%.
70.
So they're going to fill this gap using this effect.
Yes.
Is this correct?
That is absolutely correct.
And do you think it's fair, so to say, to use this kind of this reason? Because it's a matter of you absorb on the ground, but you release it.
Doesn't matter. doesn't matter. For CO2, it's one of the gases where it doesn't matter where you release it. So for CO2, because if I come back to Professor Chernyshev's contrails, they even think that if you use the contrails controlled, that is flying in human areas, producing contrails, or not flying in these areas and not producing them. But doing this at nighttime or at daytime has a different effect. So some people even speculate that by using controlled contrails, you can even reduce the impact. Global. But that's really speculation.
And in this case, your air traffic kind of changing by hour. So in the morning it's flying like this, and then all the airplanes going lower and flying. So it's like
air traffic control is a big problem because at the moment you control it by pressure level. And how do you do this in this case? It's difficult.
So I think it's
enough.
Excellent. I'd like to thank you, Professor Zodruch, for your lecture. But I'd like to address to our audience, if someone is interested in our chair, flight physics chair, to kind of do such kind of strategic planning and research, then please come to me, address to me or to Andrei Viktorovich Shustov. We'll be glad to give you some task for more complex research, multidisciplinary research, taking into account many factors, like what Professor Zodruch showed here. Это очень интересное направление, поэтому такие стратегические исследования, когда надо принимать во внимание не только сам самолет, но и систему, в которой он работает, даже видите, аэропорты там и так далее. Для нас это немножко новое, но как раз вот все преимущества, они сегодня в основном на стыке. Очень трудно внутри одной дисциплины, скажем, только аэродинамики, получить какие-то прорывные достижения, чтобы они резко изменили качество самолета, летающей техники, вертолетов и так далее. А на стыке вот таких вот разных дисциплин можно добиться большого успеха. Вот. Ну, я думаю, так, надо поблагодарить нашего гостя, профессора Зодруха.
Give our guest some small presents.
It's not so small. Thank you.
It's so-called poplanok.
And this is the.
This is.
Yeah. Okay. Well, thank you very much. It was a pleasure.
I think all of us want to ask how to obtain a job in real life.
That is easy. A job. I mean, what is easy is to come as an exchange student or to come as a DAAD student. That is easy. You even get paid for this. If you come to the DLR and bring your own money, even better. Okay, I'm joking, but if there is an interest, first of all, you go to Tsagi, okay, and ask if they allow you to come to DLR.
We would support exchange efforts, program exchange. So if, let's say, you go there, and by the way, I have time to time requests from Germany, France, NLR not NLR, but Netherlands, Delft University. Quite often requests to come here for training. The problem is that we cannot provide the same type of program, educational program, because clearance at SAGI. And you know that our research labs are located at SAGI territory, so that's a problem. But general educational course program, like our friends from India or other countries, they can be involved, and a few visits to SAGI labs also is possible. But for full-scale program, I think we need to make some other arrangements. So we have something in mind, but
No.
Exchange is fine.
But honestly, I mean, it is not as difficult as it might appear. So there are, as I said, the DAAD. If you look on, this is German exchange service. If you look on their website, and they have a specific site also for the DLR, and projects are listed there where you can apply for. I mean, you don't earn big money, but you earn a lot of experience. So it's not that difficult. No. And